Every detail in this story comes from real scientific research and observation. Tonight, we are going somewhere most people never think to look. Not down into the earth, not across the ocean, but straight up into the dark. 35 years ago, humanity launched a telescope into orbit and changed the way we understand the universe. What that telescope has seen, the distances it has measured, the light it has captured, the structures it has revealed, rewrote our understanding of how old the universe is, how fast it is expanding, and how galaxies are born and die. It has shown us things no human eye could have seen from the ground, and it is still out there right now, circling the Earth every 97 minutes, watching the sky. This channel is still new. If this kind of science feels right to you at the end of a long day, please subscribe, hit like, and turn on notifications. It helps more than you know. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. The Hubble Space Telescope was launched on April 24, 1990, aboard the Space Shuttle Discovery and placed into a low Earth orbit, approximately 547 kilometers above the planet's surface. At that altitude, it sits above nearly all of Earth's atmosphere, the layer of air that blurs and absorbs starlight before it can ever reach a ground-based telescope. From that position, Hubble can observe the universe with a clarity that no instrument on the surface of the Earth can match. It orbits at a velocity of approximately 7.5 kilometers per second, completing a full orbit of the planet in 97 minutes. In its 35 years of operation, it has made more than 1.6 million observations and contributed to over 21,000 published scientific papers. Tonight, you are going to travel with it. Not quickly, not urgently, but slowly, the way light itself sometimes seems to drift when there is no rush and no edge to reach. You are not in a hurry. There is nowhere else to be. Picture the moment of launch. It is early morning at Kennedy Space Center in Florida. The air is still cool, carrying the faint salt smell of the Atlantic off to the east. The Space Shuttle Discovery sits on Launch Complex 39B, its external tank glinting orange in the pre-dawn floodlights. Tucked inside the payload bay is a silver cylinder roughly the size of a school bus, 13.2 meters long, 4.2 meters in diameter, weighing just over 11,000 kilograms. Inside that cylinder is a primary mirror ground to a precision of 20 nanometers, 20 billionths of a meter, designed to collect light from objects billions of light years away. This is Hubble. The main engines ignite, the solid rocket boosters fire. The shuttle climbs off the launch pad and pushes upward through the blue morning air, accelerating through the sound barrier in less than a minute, shedding its solid rocket boosters at an altitude of about 45 kilometers, continuing under main engine thrust through the upper atmosphere and into the vacuum of low Earth orbit. The external tank separates, the shuttle coasts into its orbital altitude. The payload bay doors open slowly in the vacuum. And then, slowly, methodically, Hubble is released, a mechanical instrument placed gently onto an invisible current of orbital mechanics, beginning a journey around the Earth that will continue, uninterrupted, for more than 3 decades. For the first time in human history, a large optical telescope is floating free above the blurring envelope of air that has limited every astronomer since Galileo first pointed a spyglass at the sky 400 years ago. The silence out there is absolute. There is no wind, there is no weather. There is only the slow curve of the Earth below and the infinite dark above. You imagine floating alongside it. The Earth fills the lower half of your view, blue and white and vast, its surface alive with the slow motion of weather systems. You can see the curvature at the edges, the planet's limb against the black of space, outlined by the thinnest possible arc of atmosphere, a sliver of luminous blue, so thin and fragile-looking that it is difficult to believe it is the same ocean of air that feels enormous from below. From up here, the entire atmosphere, everything that supports life on the surface, every cubic meter of breathable air, is a membrane, a coating, almost nothing. The terminator, the boundary line between day and night, is a soft arc of shadow moving slowly across the surface. On the night side, you can see faint clusters of city lights scattered across continents. On the day side, cloud systems spiral over the oceans in slow, enormous wheels, driven by the Coriolis effect as the planet rotates beneath you. You are moving at 7.5 kilometers per second. In the time it takes you to draw one full breath, you have traveled about 15 kilometers. But there is no sensation of speed out here, no rushing air, no vibration, no sense of momentum. In the silence of orbital freefall, moving and standing still feel like the same thing. Hubble's main mirror is 2.4 meters across. That may not sound remarkable by earthly standards, but in space, that aperture is enough to collect light that has been traveling for billions of years and focus it onto a detector with a precision that no ground-based telescope can match. The telescope uses a Cassegrain optical design. Light enters through the front aperture, strikes the large curved primary mirror at the back, reflects forward toward a smaller convex secondary mirror positioned near the front of the tube, and is then focused back through a hole in the center of the primary mirror to the scientific instruments mounted behind it. Those instruments are housed in a compartment at the back of the telescope and include cameras, spectrographs, and fine guidance sensors. Each is designed to capture different kinds of information from the light that arrives. The fine guidance sensors alone deserve attention. They work by locking onto guide stars, stars whose positions are known to high precision, and continuously measuring any tiny deviation in the telescope's pointing direction. When a deviation is detected, a correction is sent to the reaction wheels and gyroscopes that control orientation. The result is pointing stability accurate to within 7/1000ths of an arcsecond. To translate that into physical terms, if Hubble were to shine a laser pointer from its orbital altitude of 547 kilometers, it could hold that dot fixed on a dime on the surface of the Earth. That is the level of stillness required to study a universe in which the most interesting objects are also the faintest, and the faintest objects are the most distant, and the most distant objects require hours of steady pointing to accumulate enough light for a single image. Light, when it reaches Hubble, carries a story with it. The wavelength of the light tells you how energetic it is. Shorter wavelengths like ultraviolet carry more energy. Longer wavelengths like infrared carry less. The spectrum of the light, the precise pattern of wavelengths present or absent, tells you what kinds of atoms emitted it, because each element absorbs and emits light at a specific, unique set of wavelengths. Hydrogen, the most abundant element in the universe, has a characteristic set of spectral lines. Helium, oxygen, iron, magnesium, calcium, each has its own signature, its own fingerprint in the light. And if those spectral lines are shifted, if the hydrogen fingerprint is displaced from its laboratory position toward the red end of the spectrum, that tells you the source is moving away from you. The Doppler effect shifts the wavelength of light just as it shifts the pitch of a passing siren. A source moving away from you sends its light arriving at slightly longer wavelengths. Redder, a source approaching, sends light at slightly shorter wavelengths. Bluer. In an expanding universe, nearly all distant galaxies are moving away, and the most distant ones are moving away fastest. The redshift of a galaxy's spectrum therefore serves as a proxy for its distance. The larger the redshift, the farther away the galaxy, and because light takes time to travel, the farther away the galaxy, the farther back in time you are observing. Every image Hubble takes is a picture of history. This is not a metaphor. When Hubble observes a galaxy 2 billion light-years away, the light it is collecting left that galaxy 2 billion years ago. The universe at that time was roughly 11 billion years old. On Earth, the first complex multicellular organisms, the precursors of everything alive today, were only just beginning to emerge in the shallow coastal waters of the Proterozoic oceans. Continents were in different positions, the oceans had different chemistry, and across the cosmos, in a galaxy whose light was only just beginning, a journey toward a telescope that would not be invented for another 2 billion years. Stars were being born in collapsing clouds of gas, and old stars were dying in expanding shells of expelled material. And the galaxy was doing what galaxies do across all of time, slowly evolving, slowly aging, slowly becoming something different from what it was before. That galaxy, as it exists today, is unknown to us. What Hubble sees is the galaxy as it was, frozen at the moment its light departed, that frozen image still arriving at the speed of light, still completing a journey it began 2 billion years ago. You are still floating alongside the telescope. The Earth below has grown smaller as your perspective has widened. The atmosphere is more clearly a thin film. The stars ahead are steady. No twinkling here, no atmospheric distortion, each one a fixed point of light against the absolute black. Hubble adjusts its orientation. The gyroscopes process. The reaction wheels spin, and the telescope locks onto a target and begins collecting light. In 1993, 3 years after launch, something was wrong. It had been discovered shortly after Hubble entered orbit that the primary mirror had been ground to the wrong shape. The deviation was small, only 2.2 micrometers at the outer edge, a difference about 1/50th the width of a human hair. But in an optical system as precise as Hubble's, small errors are catastrophic. The flaw produced spherical aberration, light from the outer portion of the mirror focused at a slightly different point than light from the central portion. Every image Hubble produced was blurred. Galaxies that should have appeared as crisp spirals were soft, indistinct smears. Stars that should have been sharp points were diffuse blobs surrounded by halos of misrefocused light. The telescope that was supposed to transform astronomy was returning images that ground-based instruments, using adaptive optics to correct for atmospheric distortion, could nearly match. The cause was traced to a single miscalibrated instrument used during the polishing process, the null corrector, a device that produces a precise reference wavefront for checking the mirror's shape, had one of its small lenses positioned 1.3 millimeters from its correct location. That 1.3 millimeter offset caused the corrector to report a slightly incorrect curvature profile, and the polishing team, trusting the corrector, removed material from the outer edge of the mirror until the corrector said it was perfect. The mirror was polished to exquisite precision, but it was polished to the wrong shape. 1.3 millimeters, and the most expensive scientific instrument ever launched into space, needed to be repaired. NASA designed a solution, a device called COSTAR, Corrective Optics Space Telescope Axial Replacement, was built to house 5 pairs of small mirrors, each pair positioned to intercept the light path to one of Hubble's existing instruments and correct the wavefront before it reached the detector. The mirrors in COSTAR were figured with the equal and opposite error of the primary mirror, so that the two imperfections canceled each other out. In addition, a new camera, the Wide Field and Planetary Camera 2, was built with built-in corrective optics in its relay mirrors, eliminating the need for COSTAR to service that particular instrument. The repair mission, designated STS-61, launched in December 1993 aboard the Space Shuttle Endeavour. 7 astronauts spent 11 days in orbit, over 5 spacewalks totaling 35 hours and 28 minutes. The crew installed COSTAR, replaced the wide-field camera, installed new solar arrays to replace ones that had been vibrating slightly as they moved in and out of thermal cycling between the sunlit and shadowed portions of the orbit, replaced the gyroscopes, and upgraded several other components. When the work was done and Hubble was released back into its orbit, the science team waited for the first corrected images. They were sharp, the blur was gone. Galaxies that had appeared as smeared blobs resolved into precise spirals, with individual star clusters visible along the arms. Stars that had been surrounded by halos of aberrated light became clean, precise points. The universe had been brought into focus. It was one of the most significant moments in the history of science. You think about that for a moment, drifting alongside the telescope in its orbit. A machine of this precision, this consequence returned to clarity by 7 people in pressurized suits, floating in the open vacuum above the Earth, performing surgery on an instrument that contained mirrors figured to 20 nanometers and mechanical components tolerant to fractions of a millimeter. They had trained for every step. Every tool was tethered to prevent it from floating away into orbit. Every procedure had been rehearsed underwater in the Neutral Buoyancy Laboratory at Johnson Space Center, where a full-scale model of Hubble was submerged in a pool large enough to simulate the weightless working conditions of space. It worked because people prepared for it with extraordinary patience and extraordinary care. Over the following years, Hubble was visited 4 more times. Servicing Mission 2 in February 1997 replaced 2 instruments and added the Space Telescope Imaging Spectrograph, which can capture the spectra of up to 500 astronomical objects simultaneously, and the Near-Infrared Camera and Multi-Object Spectrometer, which extended Hubble's observing capability into the near-infrared wavelengths, where many of the most distant galaxies emit most of their light. Servicing Mission 3A in December 1999 replaced all 6 gyroscopes after 3 had failed, along with a fine guidance sensor, a voltage and temperature improvement kit for the batteries, and a new computer that was 20 times faster and with 6 times more memory than the unit installed at launch. Servicing Mission 3B in March 2002 installed the Advanced Camera for Surveys, an instrument that immediately became one of Hubble's most productive, used to produce some of the most famous images the telescope has ever taken. The final servicing mission, STS-125, was completed in May 2009. Astronauts installed 2 new instruments, the Wide Field Camera 3, which operates across ultraviolet, visible, and near-infrared wavelengths, and has become one of the most capable astronomical cameras ever built, and the Cosmic Origins Spectrograph, designed specifically to study the large-scale structure of the universe through ultraviolet spectroscopy of distant quasars. They also repaired two failed instruments by replacing internal circuit boards, a task that had never been attempted on a Hubble instrument and required special repair kits built for the mission. New batteries replaced ones degraded by 18 years of charge cycles. All 6 gyroscopes were replaced again. A soft capture mechanism was attached to the base of the telescope so that a future robotic spacecraft can safely deorbit it at the end of its mission. When that crew departed and the shuttle's payload bay doors closed for the last time, Hubble was in the best technical condition of its operational life. It has been on its own ever since. No astronaut has visited it in more than 15 years. No hands have touched it, and it has continued to return extraordinary science, month after month, year after year, operating on its own in low Earth orbit above the atmosphere that blurs the view from the ground. By the time you are listening to this, in the spring of 2025, Hubble has been in orbit for 35 years. It has traveled more than 7 billion kilometers through low Earth orbit, not outward into deep space, but in circles around the Earth, accumulating distance through sheer persistence. It has looped around the planet more than 196,000 times. It has pointed at more than 55,000 distinct celestial targets, and the science drawn from those observations has appeared in peer-reviewed journals continuously across every year of its operation. That is roughly 1.5 papers published every day for 35 years. The science that has emerged from those papers has touched nearly every domain of modern astronomy and cosmology, but one of the most fundamental contributions Hubble made was to a question that astronomers had struggled with for decades: how old is the universe? Before Hubble, the age of the universe was uncertain by a factor of nearly 2. Different measurement techniques yielded values ranging from roughly 10 billion to 20 billion years. This uncertainty had an embarrassing consequence. Some age estimates placed the universe younger than the inferred ages of the oldest globular clusters within it, which was physically impossible. A universe cannot be younger than the stars it contains. The problem lay in the difficulty of measuring the Hubble constant, the parameter that describes the current rate of universal expansion. To calculate the Hubble constant precisely, you need precise distances to galaxies across a range of distances, and measuring those distances had always been limited by the blurring effect of Earth's atmosphere. Hubble was designed in large part to solve this. The method relied on a class of variable stars called Cepheid variables, stars that pulsate in brightness with periods directly related to their intrinsic luminosity. The relationship was discovered in 1908 by astronomer Henrietta Swan-Leavitt, working at the Harvard College Observatory while studying photographic plates of the Small Magellanic Cloud, a nearby satellite galaxy of the Milky Way. Leavitt noticed that the period of a Cepheid's pulsation cycle, the time it took to brighten and then dim and then brighten again, was closely correlated with the star's average absolute brightness. Brighter Cepheids pulsate more slowly, dimmer ones pulsate faster. The relationship was consistent and predictable. This was enormously useful. If you observe a Cepheid variable, measure its pulsation period, and look up the corresponding absolute luminosity from Leavitt's calibration, you know how intrinsically bright the star is. Comparing that to how bright it appears from Earth and applying the inverse square law, which states that apparent brightness falls off with the square of distance, gives you the distance directly. Before Hubble, Ground-based telescopes could only reliably detect and measure Cepheids in galaxies within roughly 10 million light-years of the Milky Way. The atmospheric blurring that smears point sources into disks made it impossible to resolve individual variable stars in more distant galaxies. Hubble changed this. With its sharp resolution and sensitivity, it could detect Cepheids in galaxies up to 50 million light-years away and beyond, reaching deep enough into the cosmic distance ladder to calibrate the Hubble constant with unprecedented precision. The result from the Hubble Key project on the extragalactic distance scale, a major observational campaign that used more than 10 years of Hubble observations to measure Cepheid distances to dozens of galaxies, was a value for the Hubble constant of approximately 72 kilometers per second per megaparsec, with an uncertainty of around 10%. A megaparsec is approximately 3.26 million light-years. So for every 3.26 million light-years of additional distance, the recession velocity of galaxies increases by 72 kilometers per second. That rate of expansion, combined with the geometry of the universe and the other components of the cosmological model, yields an age for the universe of approximately 13.8 billion years. The universe is 13.8 billion years old. That number, now refined by multiple independent measurements, including the Planck satellite's mapping of the cosmic microwave background, is one of the most precisely known quantities in science. The universe began 13.8 billion years ago in an event of extraordinary density and temperature, an event referred to as the Big Bang, and has been expanding ever since. The galaxies we observe today are not moving through space in the conventional sense, like objects thrown across a room. They are embedded in the fabric of space-time, and that fabric itself is expanding. The galaxies are carried apart by the expansion of the medium they sit in, the way dots painted on the surface of a balloon move apart from each other as the balloon is inflated, none of them moving relative to the surface they sit on, but all of them receding from each other as the surface expands. The balloon is not inflating into anything outside of itself. There is no pre-existing empty space that the universe is expanding into. The expansion is a property of space-time itself, intrinsic and simultaneous everywhere. There is no center to the expansion, no edge, no boundary. Every point in the universe experiences every other point as receding. Every observer in every galaxy looks outward and sees the same pattern. The farther away a galaxy, the faster it is moving away. And every observer is in a precise geometric sense at the center of their own observable universe. The sphere bounded by the distance light has had time to travel since the Big Bang. You, right now, wherever you are lying, are at the center of your observable universe, not metaphorically, geometrically. That is not poetry. That is the structure of a universe described by general relativity and confirmed by observation. The night around the telescope is not empty. Even in low Earth orbit, there are occasional flickers, the sun catching orbital debris, paint chips, water ice fragments, discarded hardware, drifting past at velocities of several kilometers per second. Below, the planet's surface moves through its daily rotation. Above, the stars are fixed against the black, unblinking, each one a sun, many of them surrounded by planets, some of those planets perhaps bearing chemistry as complicated as the chemistry that produced the organism now lying in the dark, breathing slowly, listening to a description of a universe that made it without knowing it was doing so. You are not in a hurry. The universe is patient, and tonight so are you. Let the details soften. Let the distances become less about comprehension and more about sensation, the sensation of being still while above you. A silver telescope watches the universe age in real time, one photon at a time, building history from the dark. Just breathe. The orbit continues. In 1995, the Hubble Space Telescope pointed at a small, seemingly empty patch of sky in the constellation Ursa Major, near the handle of the Big Dipper. The region was chosen precisely because it appeared to contain nothing, no bright stars, no nearby galaxies, no features of any kind that ground-based instruments could reliably detect. Astronomers selected it because it offered a clear line of sight out of the plane of the Milky Way, away from the gas and dust that obscures the extragalactic view in other directions. The patch occupied a region of sky about 1/30th the apparent diameter of the full moon, a circle so small that at arm's length a grain of sand held up against the sky would cover it. The telescope held that pointing position for 10 consecutive days. Over that period, it collected 342 separate exposures across 4 different wavelength filters, one in the ultraviolet, one in the blue, one in the red, and one in the near-infrared. Each individual exposure was short enough to avoid saturating the detector on any bright sources that might be present, but the exposures were combined in image processing using a technique called drizzling, which aligns and co-adds images taken at slightly different positions to achieve sub-pixel resolution and suppress noise. The total effective exposure time, summed across all frames, was approximately 100 hours. The Hubble Deep Field was released to the public in January 1996. In that small dark patch of sky that had appeared to contain nothing, the image revealed approximately 3,000 distinct objects. Nearly every single one was a galaxy. Some were spirals, their arms traced in blue and white by the light of young massive stars burning at the hottest part of the main sequence, ionizing the gas around them, illuminating the dust lanes that wove through their disks. Some were ellipticals, old, orange-gold, enormous, containing hundreds of billions of stars, but no longer forming new ones, their reservoirs of cold gas long since consumed or expelled by the energy released during the growth of the supermassive black holes at their centers. Some were irregular, their shapes distorted by gravitational interactions with neighboring galaxies, their gas compressed by the tidal forces that come when 2 massive structures pass close enough to each other that the difference in gravitational pull across their diameters begins to twist their forms. The faintest objects in the image corresponded to redshifts greater than 4, placing them at distances of more than 12 billion light-years, objects whose light had left their host galaxies when the universe was less than 2 billion years old. The Milky Way had not yet formed its current spiral structure. The solar system did not exist, the Earth did not exist, and somewhere in the early universe, a young galaxy was pouring out light that would travel for more than 12 billion years before landing on a mirror in low Earth orbit and becoming a few pixels of data in an image that would change how humanity understood its place in the cosmos. In a region of sky you could cover with a grain of sand held at arm's length, Hubble found 3,000 galaxies. The sky is not empty anywhere. You let that expand slowly, the way the universe itself expands, not as a sudden revelation, but as a continuous, quiet widening. Every dark gap between the stars visible to the unaided eye contains, behind it, galaxies, thousands of them in each gap, each containing hundreds of billions of stars, each billions of light years away, each made of the same atoms, governed by the same physics, shaped by the same gravitational interactions that shaped the Milky Way and the solar system and the planet you are lying on. The universe is not sparse. It is rich in every direction, layered with structure at every scale, from individual stars to galaxy superclusters spanning hundreds of millions of light years. That structure was not placed there randomly. It was seeded in the first fraction of a second after the Big Bang by quantum fluctuations, tiny random variations in the density of energy, that were then stretched to cosmic scales by a period of extremely rapid expansion called inflation, and amplified over billions of years by gravity, which pulled matter toward the denser regions, deepened the wells, extended the filaments, and produced the web of large-scale structure that Hubble and its successors have been mapping. The universe has architecture. It was built out of randomness and gravity and time, and it has been building itself continuously for 13.8 billion years. In 2004, a follow-up observation was made using the advanced camera for surveys installed during the 2002 servicing mission. The Hubble Ultra Deep Field imaged a region in the southern constellation Fornax for a total exposure time of approximately 1 million seconds, nearly 12 days of cumulative observing, using 4 wavelength filters and a technique that stacked hundreds of individual exposures. The resulting image revealed approximately 10,000 galaxies in a field roughly 1/13 the apparent diameter of the full moon. Some of the most distant objects in that image had redshifts above 6, corresponding to distances of more than 12 billion light years, and times when the universe was less than 1 billion years old. That era, the first billion years, is one of the most important epochs in cosmic history. It was during this period that the first stars and galaxies formed, that the intense radiation they produced began to reionize the neutral hydrogen fog that had filled the intergalactic medium since about 380,000 years after the Big Bang, the epoch of recombination, when the universe cooled enough for electrons and protons to combine into neutral atoms for the first time, making the universe transparent to light and producing the cosmic microwave background radiation that we can still detect today. Before reionization, the universe was opaque. The intergalactic medium was a fog of neutral hydrogen that absorbed ultraviolet photons before they could travel any significant distance. As the first massive stars and quasars formed and began radiating intensely, they gradually burned away that fog, ionizing the hydrogen around them in expanding bubbles that eventually merged and cleared the intergalactic medium completely by about 1 billion years after the Big Bang. Hubble was looking back to the edge of that transition, the moment when the lights first came on in the universe, when the darkness was first punctuated by the light of newly born stars, when the universe transitioned from a state of opaque uniformity to one of luminous, structured complexity. You think about the people who built the instrument capable of seeing all of this, not the engineers alone, but the entire infrastructure of human knowledge that made the instrument possible, the mathematics of optics developed over centuries, the understanding of wave interference that made precision measurement possible, the manufacturing techniques refined through decades of aerospace and defense work, the institutional patience to fund and manage a project spanning 20 years from initial concept to first light. The Hubble Space Telescope was not built quickly. The initial proposal that would become Hubble was submitted to NASA in 1946 by astronomer Lyman Spitzer in a paper titled Astronomical Advantages of an Extraterrestrial Observatory. Spitzer argued that a telescope above the atmosphere would be free of the blurring effects that limited ground-based instruments, and that the clarity gained would allow observations impossible from the surface. It took 44 years from that proposal to the launch. Spitzer lived to see it. He died in 1997 after the first servicing mission had restored Hubble's vision, after the corrected images had confirmed everything he had argued for half a century earlier. The gap between an idea and its realization in science is often measured in decades. The tools to test an idea frequently do not exist when the idea first appears. The mathematics of general relativity was complete by 1915. Gravitational waves, predicted by that mathematics, were not directly detected until 2015, exactly 100 years later, when the LIGO interferometers were finally sensitive enough to register the signal from two merging black holes. The prediction and the confirmation were separated by a century of instrument building. Hubble's story is part of that same long arc. Spitzer wrote his proposal in 1946. The telescope launched in 1990. The mirror flaw was corrected in 1993, and the science that began flowing from those corrected instruments, the age of the universe, the accelerating expansion, the deep fields, the exoplanet atmospheres, is still being analyzed and published today, 30 years after the repair mission, 79 years after the original proposal. Science is not fast, but it is persistent, and persistence over time produces clarity. You are drifting now. The effort of processing details has softened. The ideas are still here, but they are not demanding anything. They are just present, the way the light from distant galaxies is just present, arriving without urgency, without announcement, without requiring anything in return. The telescope keeps turning, the gyroscopes process, the solar panels track the sun, the data flows down to White Sands, New Mexico, where large dish antennas receive the radio signal, and from there to the Space Telescope Science Institute in Baltimore, Maryland, where a staff of scientists and engineers translates photons into calibrated archived data, made available to researchers anywhere in the world. The archive keeps growing, published continuously, steadily, for 35 years, every paper in it built on light that came from somewhere else, from a dying star, a forming planet, a distant galaxy, a quasar blazing at the center of a structure that no longer exists in its current form. The universe speaks, Hubble listens, and the papers are the translation. Most of the time, what Hubble sees builds slowly, an image that requires hours of cumulative exposure time across multiple visits to the same patch of sky, the telescope returning each time and adding another layer of photons to the accumulating signal, the faint structure at the edge of detection becoming clearer with each added observation, the way a shoreline becomes visible in fog as you move closer, not suddenly, but gradually, detail by detail. This is how the universe reveals itself, not in a flash, not in a single moment, in an accumulation of small signals, each one arriving at the speed of light, none of them in a hurry, all of them carrying information about a time and a place that no longer exists in the form it held when the light departed. You are not in a hurry either. Let your breathing slow even further. Let your body grow heavier in the way that comfortable bodies do when they are close to sleep. Not heavy with effort, but heavy with stillness, with the permission to stop moving. The universe outside is doing what it has always done. Stars are forming in molecular clouds where hydrogen densities have crossed the threshold at which gravity overcomes thermal pressure, and the gas begins to collapse. In the cores of those forming stars, temperatures are rising toward the 10 million degrees Kelvin required to initiate nuclear fusion, the process that converts hydrogen to helium and releases the energy that holds stars in hydrostatic equilibrium for millions or billions of years, depending on their mass. Massive stars burn hot and fast. A star 20 times the mass of the Sun will exhaust its hydrogen fuel in a few million years, expanding into a supergiant, fusing progressively heavier elements: helium, carbon, oxygen, neon, silicon, in successive shells around the core, until the core accumulates enough iron that fusion no longer releases energy and the core collapses in a fraction of a second, triggering a supernova explosion that ejects the outer layers into the interstellar medium at velocities of 10,000 kilometers per second, seeding the surrounding gas with the heavy elements forged during the star's life and during the explosion itself. The oxygen in your lungs right now was synthesized in the core of a massive star during the silicon burning phase of stellar evolution and scattered into the interstellar medium when that star died. The iron in your blood was produced in a core collapse supernova. The calcium in your bones, the phosphorus in your DNA, the trace metals in your cells, all forged in stellar cores, all scattered by stellar deaths, all eventually incorporated into the molecular cloud that collapsed to form the solar system 4.6 billion years ago. You're not an observer of the universe. You are a product of it. You are a temporary configuration of stellar material assembled by chemistry and biology over 4 billion years of evolution on a small rocky planet, briefly capable of consciousness and language and the ability to build instruments that can read the history of the universe from the light that arrives. That is not a small thing, but it is a quiet one. And tonight, in the quiet, you do not need to hold any of this with effort. The universe will be exactly as large tomorrow as it is tonight. The galaxies will still be there. The telescope will still be there, circling the Earth in its 97-minute orbit, watching the sky, collecting photons, returning data. Let it all soften now. Let the numbers dissolve into sensation, the sensation of being very small in a very large place, and finding that smallness comfortable rather than frightening. The darkness behind your closed eyes is the same darkness between the galaxies. The stillness in your body is a version of the stillness at the edge of the observable universe, where the last detectable signals are fading into wavelengths too long for any instrument to read. You are part of this. You are resting inside it. Breathe in, hold for just a moment, let it out. The orbit continues, the gyroscopes hold. Hubble turns to its next target, and somewhere in the dark above the atmosphere, the universe continues to pour its ancient light into a mirror 2.4 meters wide, and that light becomes a signal, and that signal becomes data, and that data becomes understanding, and that understanding becomes part of what it means to be alive in this particular window of cosmic time, this brief, lucky era when the universe is still young enough that its light can still reach us from everywhere. You are here for all of it, even now, especially now. Rest. Let sleep come the way starlight comes, not all at once but gradually, one photon at a time, building something luminous out of what was dark, arriving without urgency, without announcement, without asking anything in return. You are nearly there. Just breathe. The night is long and the universe is 13.8 billion years old, and right now, none of it asks anything of you. Just this. Just the slow, comfortable weight of your body settling deeper, the details of everything softening at the edges, the distances becoming something closer to peace. The orbit continues. Hubble watches, and you drift. You are still here, still drifting, still carried gently by the orbit of an idea that has not finished moving through you. The telescope is still above you. The universe is still unfolding, and there is more to see. There is a particular kind of observation that Hubble has made more than almost any other, one that looks at first glance like a flaw in the image. In photograph after photograph of massive galaxy clusters, you will notice curved arcs of light arranged in rings and partial bands around the central mass of the cluster. They are not artifacts. They are not lens flares or reflections or imperfections in the optics. They are the distorted images of galaxies that lie far behind the cluster, galaxies whose light is being bent by the gravitational field of the foreground cluster as it travels through on its way to the telescope. The phenomenon is called gravitational lensing, and it was predicted by Albert Einstein's general theory of relativity in 1915. General relativity describes gravity not as a force transmitted instantaneously between objects, not in the way Newton conceived it, but as a curvature in the geometry of space-time itself. Mass and energy warp the four-dimensional fabric of the universe around them, and objects moving through that warped geometry follow curved paths. Photons of light, which have no mass but do carry energy and momentum, also follow those curved paths. A massive object like a galaxy cluster does not pull light toward it in the classical sense. It curves the space through which the light is traveling, and the light, following the straightest possible trajectory through curved geometry, bends around the mass. From a distance, the effect produces images that look exactly like the distortions produced by an imperfectly shaped glass lens, elongated, curved, sometimes split into multiple copies of the same source, hence the name gravitational lensing. Einstein calculated in 1936 that a star perfectly aligned behind another star should produce a circular ring of light, what is now called an Einstein ring, as the background star's light bends around the foreground star's gravitational field and reaches the observer from all directions equally. He published this result alongside his calculation, but dismissed the phenomenon as a mathematical curiosity. The angular scales were far too small, he believed, for the telescopes of his time to resolve, and perfectly aligned objects, which would require precise alignment along a single line of sight extending across light years, seemed too rare to expect in practice. He was wrong on both counts. Hubble has imaged complete Einstein rings, arcs that close into full or nearly full circles around a foreground galaxy. It has imaged partial arcs, split images, and the spectacular blue arcs that appear in deep images of massive galaxy clusters like Abell 2218, Abell 370, and the Hubble Frontier Fields clusters, including MAX J0416 and MAX J0717. In each of those images, the blue arcs are not separate objects. They are the bent, stretched, magnified images of individual background galaxies, sometimes a single galaxy appearing as 2 or 3 or 4 separate arcs arranged around the foreground cluster, each a different image of the same object, produced by different paths the light has taken around the cluster's gravitational well. The color of those arcs, the blue, is not an artifact of the lensing. It reflects the true color of the background galaxies. Blue galaxies are galaxies in which new stars are actively forming. Young, massive, hot stars emit most of their energy at blue wavelengths. The background galaxies visible as lensed arcs in cluster images tend to be young, actively star-forming systems observed at large redshifts. Early universe galaxies caught in the process of building themselves from gas, their blue light stretched and bent by the intervening cluster and delivered, amplified to Hubble's detectors. Gravity bends light, and Hubble has spent 35 years watching it happen. The clusters that produce the most dramatic lensing effects are among the most massive structures in the observable universe. A massive cluster contains hundreds to thousands of individual galaxies, each galaxy containing hundreds of billions of stars, the whole assembly embedded in a diffuse halo of plasma heated to tens of millions of degrees by the gravitational compression of the gas as the cluster assembled. Plasma so hot that it glows at X-ray wavelengths, invisible to Hubble but detectable by space-based X-ray observatories like Chandra, and surrounding all of the visible matter, extending far beyond the edges of the visible galaxy distribution, is the dominant component, dark matter, whose total mass typically exceeds the visible matter in the cluster by a factor of 5 to 7. Dark matter does not emit, absorb, or reflect electromagnetic radiation of any kind. It cannot be directly detected by any camera, spectrograph, or detector ever built. Hubble cannot see it. No telescope can. It interacts with ordinary matter only through gravity, and yet it constitutes approximately 27% of the total energy content of the universe, more than 5 times the mass of all the ordinary atoms that have ever assembled into stars, galaxies, gas clouds, planets, and organisms across the entire observable universe. The only way to detect dark matter is through its gravitational effects on things that can be seen. Gravitational lensing provides one of the most direct and geometrically transparent methods for doing this. When a background galaxy is gravitationally lensed by a foreground cluster, the distortion in the galaxy's apparent shape is determined by the gradient of the gravitational potential at the galaxy's position in the plane of the sky. By precisely measuring the shapes, orientations, and positions of thousands of background galaxies behind a cluster, and analyzing the statistical patterns in those measurements, scientists can reconstruct the distribution of gravitational potential and therefore mass across the cluster, including the mass that is not directly visible. The technique is called weak gravitational lensing, when the individual distortions are too small to see by eye, requiring statistical analysis of many background sources. It is called strong gravitational lensing, when the geometry is favorable enough to produce the dramatic arcs and rings visible in individual images. Hubble has applied both approaches extensively, mapping dark matter distributions in dozens of clusters and contributing to surveys of large-scale dark matter structure across hundreds of millions of light-years. The Hubble Frontier Fields program, completed in 2016, was one of the most ambitious applications of this approach. It produced the deepest images ever obtained of 6 carefully selected massive galaxy clusters, using approximately 840 orbits of Hubble time, each orbit a full loop around the Earth, accumulated over multiple years. The clusters were chosen for their strong lensing power, maximizing the natural magnification they provided for background sources. Each cluster field was observed alongside a parallel field slightly offset from the cluster, where the sky was relatively blank, providing an unobstructed view to equivalent depths for comparison. The program simultaneously produced detailed dark matter maps of the 6 clusters and used those clusters as natural gravitational telescopes to detect background galaxies at redshifts that would have been impossible to observe without the lensing amplification. Some of the background galaxies detected in the frontier fields images have redshifts above 9, corresponding to distances of more than 13 billion light-years and times less than 600 million years after the Big Bang. These are among the most distant objects ever confirmed, observed because a massive foreground cluster happened to lie along the line of sight and amplified their light by a factor of tens to hundreds. The universe provided its own lenses, and Hubble pointed at them. You think about what it means to map something invisible, to infer, from the distortions in the light of distant galaxies, the distribution of matter that no instrument can directly detect. Every dark matter map produced from gravitational lensing is a picture drawn entirely from inference, not from observation of the dark matter itself, but from the footprint it leaves on the light that passes through the space it occupies. This is how science extends its reach beyond the directly observable, not by accepting ignorance, but by finding what each invisible thing leaves behind: a velocity, a deflection, a temperature, a timing difference, a distortion, and then following that trace back to its cause. Dark matter leaves traces everywhere astronomers look. In the rotation curves of spiral galaxies, the measured velocities of stars at different distances from a galaxy's center, which remain nearly constant at large radii, rather than declining as expected if only the visible matter contributes to the gravitational field. In the velocity dispersions of galaxies within clusters, which imply cluster masses far exceeding what the visible stars and gas could account for. In the angular power spectrum of the cosmic microwave background, where the relative heights of the acoustic peaks encode the ratio of dark matter to ordinary matter in the early universe, and the lensing distortions that Hubble has mapped across the sky. Every measurement points in the same direction. Something is there. It is everywhere, and we do not know what it is. That is not a failure of science. That is science at work, identifying something real, constraining its properties, ruling out possibilities, and building the foundation for the observations and experiments that will eventually reveal its nature. You are lying still. Your breathing is slow and regular. The details of the day are no longer pressing. The ideas moving through you have softened at the edges, the way stars soften at the edge of a long exposure photograph, still present, still real, but blurred by time and accumulation into something that feels more like atmosphere than information. The telescope above you keeps its orbit. The gyroscopes hold their lock, 97 minutes per orbit, completed more than 196,000 times since 1990. Hubble has observed phenomena at every scale available to an optical and near-infrared telescope in low Earth orbit. At the largest scales, it has mapped the distribution of galaxies and dark matter across hundreds of millions of light-years. At the smallest scales accessible to its optics, it has resolved individual stars in nearby galaxies, tracked the positions of stars in the central parsec of the Milky Way's nuclear star cluster, and even observed surface features on the largest asteroids. In between those extremes, it has watched things happen in real time in ways that no previous telescope was positioned to witness. In July 1994, Hubble observed the impact of comet Shoemaker-Levy 9 with Jupiter. The comet had been discovered in March 1993 by astronomers Carolyn and Eugene Shoemaker and David Levy using a photographic survey at Palomar Observatory. When the discovery images were examined, The comet appeared stretched into a chain of fragments, unusual and striking in shape. Analysis of the orbits of the fragments established that the comet had passed extremely close to Jupiter in July 1992, well within the Roche limit, the distance at which tidal forces from Jupiter exceed the internal self-gravity of the comet. The encounter had torn the comet apart. By the time of its discovery, it had fragmented into at least 21 distinct pieces, arranged in a chain that orbital mechanics was carrying back toward Jupiter on a collision trajectory. The impacts occurred over 6 days, from July 16th to July 22nd, 1994. 21 fragments, designated alphabetically from A to W, struck Jupiter's atmosphere in sequence at intervals of a few hours to a full day between impacts. The collision velocities were approximately 60 kilometers per second, more than 17 times the speed of a rifle bullet. Hubble observed every impact for which observing time could be arranged. The fireballs rising above Jupiter's cloud tops were visible even to some ground-based telescopes, but Hubble's resolution revealed the structure of the impact sites in detail unavailable from the ground. The dark scars that formed were regions of Jupiter's upper atmosphere, disrupted by the energy of impact and stained by sulfur compounds and dark organic materials lifted from the deeper atmosphere. Several scars were each individually comparable in size to the Earth. Hubble continued to image the impact sites over the weeks and months that followed, tracking the spreading and fading of the dark patches as Jupiter's atmospheric winds dispersed them. The entire sequence, from impact to dispersal, was documented in a way that no prior planetary event had ever been documented. Jupiter's role as a gravitational shield for the inner solar system became, through that observation, something more than a theoretical claim. It was demonstrated visibly in the scale of what arrived at Jupiter and the energy with which it arrived. The dynamics of the solar system are not static. Objects move, orbits intersect, and the presence of a massive planet at the right location in the solar system has, over the billions of years of Earth's existence, diverted many impactors that might otherwise have reached the inner planets. Hubble has also watched the ongoing process of stellar birth. In the Eagle Nebula, a region of active star formation approximately 6,500 light-years from Earth, in the constellation Serpens, Hubble imaged in 1995 a structure that became one of the most widely reproduced astronomical photographs ever produced. 3 tall columns of gas and dust, each several light-years in height, rising from a larger cloud and illuminated from above by the intense ultraviolet radiation of newly formed massive stars nearby. The columns, called elephant trunks or evaporating gaseous globules, depending on the feature, are regions where the density of gas is high enough to partially resist the photoevaporation driven by the ultraviolet radiation. Inside them, protected from the most intense radiation by the density of the surrounding material, small dense clumps of gas called eggs, evaporating gaseous globules, may contain newly forming protostars. The image, known informally as the Pillars of Creation, showed the process of star formation in a way that had never been directly imaged before. The physical environment in which gravity and radiation and gas dynamics interact to produce the conditions for collapse, the moment at which the universe is building new suns from gas and dust. The image was updated with new, higher-resolution observations from Hubble's Wide Field Camera 3 in 2015, and again by the James Webb Space Telescope in 2022, which imaged the region in infrared wavelengths, penetrating the gas and dust to reveal the interior structure in detail that optical wavelengths cannot access. But it was Hubble's 1995 image that introduced the pillars of creation to the world, that made the process of star formation visible in a way that could be seen and remembered. This is where stars are born. The gas and dust in the Eagle Nebula's pillars is the same raw material that formed the Sun 4.6 billion years ago. The same kind of molecular cloud, the same hydrogen and helium enriched with the heavier elements produced by previous stellar generations. The same gravitational instability that begins the collapse of a dense clump. The process playing out in the pillars of creation today is the same process that, billions of years ago, produced the nebula from which the solar system assembled. The timescale for that process, from collapsing cloud to main sequence star, is roughly 1 to 10 million years, depending on the mass of the star forming. That sounds long, but against the backdrop of the 13.8 billion year age of the universe, it is a very brief transition. The cloud spends millions of years in a state of slow, dense quiescence. Then gravity wins, and within a cosmologically short period, a protostar ignites. The disk of gas and dust that forms around it coalesces into planets over tens of millions of years. And those planets can persist, geologically active or quietly cooling, for billions of years after that. The Sun itself has been burning for approximately 4.6 billion years and has roughly 5 billion years remaining before it expands into a red giant. By cosmic standards, it is middle-aged. The process that created it, the collapse of a molecular cloud enriched by the contributions of previous stellar generations, is the same process visible in the Eagle Nebula today, playing out in a different cloud, at a different location in the galaxy, in what is, cosmologically speaking, almost exactly the same era. The pillars of creation are not a historical document. They are a live transmission from the universe's ongoing act of self-construction. Your breathing is very slow now. The room is quiet. The weight of your body is comfortable, settled, still, not going anywhere. The telescope is above you. The dark is above the telescope, and beyond the dark, at distances described by numbers too large to hold in a single thought, the universe is doing what it always does, making stars from gas, burning them for millions or billions of years, and returning their material to the interstellar medium when they die, enriched with whatever elements they had time to produce. There is still more that Hubble has seen. You do not have to hold it all. Let it arrive the way the light arrives, without pressure, without deadline, at whatever pace the orbit allows. Hubble has contributed to the study of exoplanet atmospheres, a domain that was entirely beyond its original design goals, because when Hubble was conceived in the 1970s and designed through the 1980s, no planets outside the solar system had been confirmed. The first detection of an exoplanet orbiting a main sequence star was not made until 1995, when Michel Mayor and Didier Queloz of the Geneva Observatory announced the discovery of 51 Pegasi b using the radial velocity method, measuring the periodic Doppler shift in the star's spectral lines caused by the gravitational tug of the orbiting planet. The planet was a gas giant roughly half the mass of Jupiter, orbiting so close to its host star that its orbital period was only 4 days. Nothing in solar system experience had prepared astronomers for planets of this kind. Massive gas giants in extremely tight orbits around sun-like stars, with surface temperatures exceeding 1,000 degrees Celsius. Dozens, then hundreds, then thousands of exoplanets were confirmed in the following years, discovered primarily by the radial velocity method and later by the transit method, detecting the slight dimming of a star's light when a planet passes in front of it, as seen from Earth. The Kepler Space Telescope, launched in 2009, surveyed more than 150,000 stars for transiting planets over 4 years, and produced a catalog of thousands of confirmed planets and planet candidates across a vast range of sizes, orbital periods, and stellar types. Hubble could not directly image most exoplanets. They are too faint and too close to their host stars for the contrast to be resolved at the angular separations involved. But it could do something subtler. When a transiting planet passes in front of its host star, it blocks a fraction of the star's light, proportional to the ratio of the planet's cross-sectional area to the star's. If the planet has an atmosphere, that atmosphere extends beyond the solid body of the planet and absorbs starlight at wavelengths corresponding to the absorption lines of whatever molecules are present. The effective size of the planet, as seen in transit, is wavelength dependent, larger at wavelengths where atmospheric gases absorb, smaller at wavelengths where the atmosphere is transparent. By measuring the transit depth at multiple wavelengths, essentially taking a spectrum of the star in and out of transit and looking for wavelength-dependent changes, scientists can infer the composition of the planet's atmosphere. This technique is called transmission spectroscopy. Hubble made the first detection of an exoplanet atmosphere in 2001, observing the hot Jupiter HD 209458b during transit and detecting sodium absorption in the planet's upper atmosphere. It subsequently detected hydrogen, oxygen, carbon, and in multiple separate observations, water vapor, the spectroscopic signature of H2O absorption in the near-infrared in the atmospheres of several exoplanets. These were the first direct measurements of chemical compositions in worlds beyond the solar system. The implications reach toward one of the oldest questions in human thought. Are we alone? Hubble's exoplanet atmospheric detections were all made in gas giants, HD 209458b, HD 189733b, WASP 12b, planets too large and too hot to support anything resembling the chemistry of life as we understand it. Water vapor in a 1,000-degree atmosphere is not a biosignature, but the technique Hubble pioneered, measuring atmospheric absorption during transits, is the same technique that the James Webb Space Telescope is now applying to smaller, cooler, rocky planets. Webb has already detected carbon dioxide, sulfur dioxide, and water vapor in the atmospheres of several planets in the TRAPPIST-1 system, a collection of 7 rocky planets orbiting an M-dwarf star approximately 40 light-years from Earth, 3 of which lie within the star's habitable zone, the range of orbital distances where liquid water could exist on a planet's surface if conditions are otherwise favorable. Webb has not yet detected biosignatures in those atmospheres. The observations are difficult, requiring many transits, careful modeling of the stellar spectrum, and the ability to distinguish genuine planetary atmospheric signals from stellar noise. But the capability is being developed. The tools are being refined. The observations are accumulating. There is something worth noting about the relationship between Hubble and its successor. The James Webb Space Telescope is more powerful than Hubble in many respects. Its primary mirror is 6.5 meters across, more than 6 times the collecting area of Hubble's 2.4-meter mirror. It operates primarily in the infrared, which allows it to see through dust and observe the most distant galaxies with a clarity Hubble cannot match. It is positioned not in low Earth orbit, but at the second Lagrange point of the Earth-Sun system, 1.5 million kilometers from Earth, where it can maintain a stable thermal environment and observe continuously without the interruptions of Earth's shadow. And yet Hubble has not been retired. The two telescopes are operating simultaneously, often observing the same targets in complementary wavelengths. Hubble covers the ultraviolet and blue visible wavelengths that Webb cannot observe. Webb's instruments are designed for infrared, and a cold telescope optimized for those wavelengths does not observe efficiently in the ultraviolet. Hubble's ultraviolet capability is irreplaceable by any currently operating instrument. There is no other telescope in orbit with comparable sensitivity at those wavelengths. Ultraviolet light carries specific and essential scientific information. Many of the most important spectral features of hot stars, active galactic nuclei, and the intergalactic medium fall in the ultraviolet. The Lyman alpha line of hydrogen, the transition from the first excited state to the ground state, emitting at 121.6 nanometers, is one of the most useful tracers of hydrogen gas in the universe, and it falls in the ultraviolet at most redshifts accessible to Hubble. The Cosmic Origins spectrograph, installed in 2009, was designed specifically to observe this line and other ultraviolet spectral features in the spectra of distant quasars, using the quasar light as a backlit probe of the gas structures, the intergalactic filaments of the cosmic web that lie between the quasar and Earth. Those observations have produced some of the most precise measurements ever made of the distribution of ordinary baryonic matter in the large-scale structure of the universe. Most of the ordinary matter in the universe, the atoms, the gas, everything that is not dark matter or dark energy, does not reside in galaxies. It resides in the intergalactic medium, in the diffuse filaments of the cosmic web, at temperatures between 10,000 and 10 million degrees Kelvin, emitting and absorbing primarily in the ultraviolet. Ground-based telescopes cannot observe at these wavelengths. Earth's atmosphere absorbs ultraviolet light almost completely below about 300 nanometers. Only a space-based instrument can access this spectral window. Hubble is the only instrument currently operating that can do so at the required sensitivity. For as long as it functions, it provides a view of the universe that Webb cannot provide, that no ground-based telescope can provide, that will be lost, at least temporarily, when Hubble finally ceases operation. This is part of why scientists continue to use it, continue to propose for time on it, continue to publish from its archive, even as Webb produces results that would have seemed impossible a decade ago. Each instrument has its domain. Each instrument sees a part of the universe that the others cannot. You lie still and let that register quietly, not as urgency, not as something requiring attention, but as a fact about the way science works at the frontier, with many instruments listening simultaneously in different wavelengths, each one extending the range of what can be known, each one handing off to the next when its operational life ends, the archive of what it recorded, remaining accessible long after the instrument itself has gone dark. Hubble opened that door. It demonstrated that transmission spectroscopy was possible, that exoplanet atmospheres were accessible to telescopes, that the composition of worlds around other stars was not permanently beyond reach. Every Webb detection of an exoplanet atmosphere builds directly on the techniques Hubble developed, calibrated, and proved across 25 years of exoplanet observations. The question of whether life exists elsewhere in the universe does not yet have an observational answer, but it has moved, in the lifetime of the Hubble Space Telescope, from a question that could only be asked philosophically to one that is being approached with real instruments and real data. That is a profound transition. You do not need to hold all of this in your mind right now. Let it settle. Let it sit in the background, the way the cosmic microwave background sits in the background of the universe, always present, always carrying information, not demanding attention but available to any instrument sensitive enough to read it. The night is very quiet now. One of the most important things Hubble has done over 35 years is document change. Not just the static universe, not just what the universe looks like at one moment, but how it has evolved across cosmic time, what it looked like at different epochs, how galaxies form and age and merge and die. This is possible because distance and time are the same thing for light. When Hubble observes a galaxy at a redshift of 1, meaning its light has been stretched to twice its emitted wavelength by the expansion of the universe, it is observing that galaxy as it existed roughly 8 billion years ago, more than halfway back to the Big Bang. When it observes a galaxy at a redshift of 3, it is looking back to a time when the universe was roughly 2 billion years old, less than 1/6 its current age. By assembling a catalog of galaxies observed at many different redshifts, many different distances, many different look-back times, Hubble has produced something like a fossil record of galaxy evolution, snapshots of the universe at many different ages, which can be compared to understand how the galaxy population has changed across cosmic time. What that record shows is striking. At high redshifts, in the early universe, when it was 2 to 4 billion years old, the galaxy population was dominated by small, irregular blue galaxies, compact systems with active star formation, disturbed morphologies, abundant cold gas. Galaxies at that epoch were not like the large settled spirals and ellipticals that dominate the universe today. They were smaller, bluer, more chaotic, actively building their stellar populations through rapid star formation and frequently interacting with neighbors. At lower redshifts, closer to the present, the galaxy population looks very different. Many of the most massive galaxies are large red ellipticals, old passively evolving systems that formed most of their stars billions of years ago and have since stopped forming new ones, their star-forming gas exhausted or expelled. The spirals that make up much of the present galaxy population, including the Milky Way, show complex structure, bulges, disks, arms, bars, central concentrations of old stars, ongoing star formation in the arms, and evidence of past mergers in their kinematics and stellar populations. The transition between these two states, from the active, irregular, gas-rich early universe to the more settled, morphologically diverse present-day universe, happened gradually and not uniformly. Different galaxies evolved on different timescales, shaped by their mass, their environment, the properties of their central black holes, and the random history of their mergers and interactions. Hubble's imaging of galaxies across a wide range of redshifts, combined with spectroscopic follow-up from ground-based telescopes, has been central to building the empirical picture of galaxy evolution. The Cosmic Evolution Survey, known as COSMOS, used Hubble to image a large area of sky, roughly 2 square degrees, with high resolution and sensitivity, producing a catalog of hundreds of thousands of galaxies at a range of redshifts, each with measured morphology and photometric properties. That catalog has been the basis for hundreds of papers, examining how the size, structure, color, star formation rate, and clustering of galaxies have changed across cosmic time. The story those papers tell is coherent with the theoretical picture of hierarchical structure formation. In a universe dominated by dark matter, small structures form first, and large structures form later, through the successive merging of smaller ones. Small galaxies formed early and merged into larger ones over time. The most massive elliptical galaxies, which contain the oldest stellar populations and are found preferentially in the densest environments, the centers of rich galaxy clusters, formed through the merging of many smaller predecessors. The large spirals formed somewhat later and have been more quiescent since, building their disks gradually through the accretion of cold gas. Mergers between galaxies are not gentle. When two galaxies of comparable mass interact gravitationally over millions to hundreds of millions of years, the tidal forces disrupt their ordered structures, pulling streams of stars and gas into arcs and bridges that can extend hundreds of thousands of light years from the main bodies. The cold gas in both galaxies is compressed by shocks, triggering bursts of star formation at rates far higher than the galaxies would sustain in isolation. The two central black holes, each at the center of one of the merging galaxies, eventually spiral toward each other through dynamical friction, and in the final stages of the merger, they will coalesce in an event that releases gravitational waves, ripples in the space-time fabric of extraordinary amplitude. Hubble has imaged galaxy mergers in many different stages. The antennae galaxies, a famous pair of interacting galaxies in the constellation Corvus, designated NGC 4038 and NGC 4039, located about 45 million light-years from Earth, show two galactic nuclei surrounded by a chaos of star-forming regions, blue and pink with the light of newly formed massive stars and the glowing hydrogen gas they ionize, with long tidal tails extending far from the main bodies like antennae. The tails are made of stars pulled from the outer disks of both galaxies by the tidal forces of the interaction, arcing through space on trajectories that will take hundreds of millions of years to play out. Hubble's images of the antenna, taken at multiple epochs over the years, reveal individual star clusters forming within the compressed gas of the merger, clusters containing hundreds of thousands of stars, born within the last few tens of millions of years in the enhanced star formation triggered by the collision. These young clusters are so bright and compact that they appear as individual points of light in Hubble's images. Stellar nurseries resolved into distinct objects, each one a seed of stars that will disperse across the galaxy over the next few billion years. The Milky Way is not immune to this process. Astronomical observations and dynamical simulations consistently predict that the Milky Way and the Andromeda Galaxy, our nearest large spiral neighbor, located approximately 2.5 million light-years away and approaching at roughly 110 kilometers per second, will begin their first close encounter in approximately 4 billion years. The interaction will unfold over billions of years, with multiple close passes and eventual coalescence into a single large elliptical galaxy. The Sun will likely be flung to a larger orbit during the interaction, but will probably survive, orbiting the remnant galaxy in a region of space far from the dense central merger. The probability of an actual collision between individual stars, which are separated by vast distances even within a dense galaxy, is extremely low. The merger of the Milky Way and Andromeda is inevitable given enough time, and enough time is what the universe has in abundance. You let that settle, not urgently, not with the need to process it fully, but as a piece of context about the planet you are resting on, a planet in a solar system that belongs to a galaxy that is on the timescale of billions of years in the early stages of a cosmic encounter with its nearest large neighbor. Everything is in motion. Everything is changing. The appearance of stability is the appearance of a process unfolding on timescales too long for any individual observer to witness as change. The mountains outside are moving very slowly, driven by the tectonic processes that have been reshaping the continents for billions of years. The stars in the sky are moving very slowly, drifting through the galaxy on their own orbital paths around the Milky Way's center. The galaxies in the local group are moving, converging over billions of years toward a future merger, and the distant galaxy clusters are receding, carried apart by the expansion of space, moving away from each other at rates that increase with distance. Everything is in motion, and yet right now, right here, everything feels very still. There is a quality to late-night quiet that is different from the quiet of early evening. It is deeper, more settled. The ambient sounds have faded. The sounds of movement, of voices, of machinery have receded. The quiet that remains is not the absence of sound, but the presence of a stillness that is closer to the state of interstellar space, where the density of matter drops to less than 1 atom per cubic centimeter, where the temperature of the gas is only a few degrees above absolute zero, where the primary sound is not sound at all, but the microwave hiss of the Big Bang's afterglow, still filling the universe at a temperature of 2.725 Kelvin. The night sky above the clouds is not silent in that physical sense. It is full of radio waves, X-rays, cosmic rays, the constant rain of neutrinos from the sun and from supernovae across the galaxy. But to human senses, in the dark of a quiet room, it is still, and that stillness has a depth to it that extends outward beyond the walls, beyond the atmosphere, beyond the solar system and the galaxy, all the way to the edge of the observable universe. You are resting at the bottom of a gravitational well on the surface of a rocky planet. The well is shallow by cosmic standards, shallow enough that you can lie here comfortably, that your bones support your body weight, that the atmosphere stays bound to the planet and remains breathable. But it is a real gravitational well, described by the same equations that govern the curvature of spacetime around galaxy clusters and the orbital mechanics of Hubble and the expansion of the universe itself. General relativity does not stop working at any particular scale. The curvature of spacetime exists right here, right where your body is lying. A clock on the floor of a room runs very slightly slower than a clock on a shelf a meter higher. The difference is immeasurable in everyday life, about 1 part in 10 to the 16th per meter of altitude, but it is real and it has been measured. GPS satellites must correct for both the relativistic time dilation due to their velocity and the gravitational time dilation due to their altitude above the Earth's surface, or the accumulated error over a single day would make the positioning system useless. The physics does not change between scales. The same curvature of spacetime that bends light around a galaxy cluster also bends light very, very slightly around the Earth, around the mass of your own body, around every atom in the room. The universe is described by a single set of equations that apply everywhere, at every scale, without exception. You are resting inside the same universe that Hubble photographs. Not above it, not outside it, not separated from it by any boundary. Inside it, part of its inventory, made from the same matter that fills the galaxy clusters and the stellar nurseries and the supernova remnants and the hydrogen clouds from which new stars will eventually form. Let that be a quiet thing, not a thing that requires thought or response, just a thing that is true, the way the expansion of the universe is true, and the age of the stars is true, and the darkness of the night sky is true, facts that do not demand anything of you, that will remain exactly as they are, whether you hold them consciously or release them entirely. Release them. Let the details dissolve. Let the numbers become distances, and let the distances become something wider than numbers, something that has the texture of the dark between galaxies, the particular quality of emptiness that is not empty at all but structured, threaded through with the geometry of space-time and the invisible mass of dark matter and the ancient light of the cosmic microwave background, 2.725 degrees above absolute zero in every direction, the oldest signal in the universe, still arriving. Your body is very still. Your breathing is very slow. The room around you has grown completely quiet. The orbit continues, the gyroscopes hold, the data flows, and Hubble watches the sky with the same precise, patient attention it has maintained for 35 years. The same attention that produced the Hubble Deep Field and the corrected images after the 1993 servicing mission, and the Cepheid distance measurements, and the supernova observations that revealed the accelerating expansion, and the gravitational lensing maps, and the pillars of creation, and the atmosphere of HD 209458b, and the star at 12.9 billion light-years, and more than 21,000 scientific papers, and more than 1.6 million observations, and more than 196,000 orbits of a planet that, from an altitude of 547 kilometers, fits within the span of a single sweeping view. The Earth is very beautiful from up there, the blue of the oceans, the white of the cloud systems, the brown and green of the continents, the thin, luminous arc of the atmosphere at the edge of the limb, the slow rotation, the shadow of night moving across the face of the planet as it turns. And below the atmosphere, in the quiet of a dark room somewhere on the surface, a person is lying still, breathing very slowly, almost asleep, carrying the universe gently in the background of a mind that is preparing to let go of everything for a while. You, just here, just this breath, just the weight of your body in the position it has settled into. The universe is very old, the night is very quiet, and you are exactly where you are supposed to be. Let sleep come. Let it come the way the cosmic microwave background arrives, everywhere at once, from every direction simultaneously, not asking for anything, just present, just filling the space available, just doing what it has been doing since the beginning. You are nearly there. Everything you heard tonight is real. Hubble is out there right now. 35 years in orbit, still watching, still collecting, still sending light back home, from the edges of the observable universe, from the surfaces of distant planets, from the remnants of dead stars, from the nurseries of stars not yet born, still building, paper by paper, observation by observation, the most detailed picture of the universe that any instrument in human history has ever assembled. All of it real, all of it continuing, the archive growing, the science proceeding. And tonight, none of it asks anything of you. You have listened, you have carried it gently through the hours of the night, and now you can set it down entirely, the way you set down the events of the day, the way the universe sets down the energy of a dying star and carries it forward as the motion of an expanding shell of gas that will eventually become part of something new. Nothing is lost. Everything continues, and you can rest. If tonight felt like the right way to end a day, if this is how you want to move towards sleep, with the real universe as company, please subscribe to Quiet Science at Bedtime. Leave a like if this helped you rest, and turn on notifications so you do not miss what comes next. There is more distance, more deep time, more phenomena stranger, and more beautiful than anything invented. All of it real, all of it waiting. But not tonight. Tonight you sleep. Good night. Sleep well. The orbit continues.